In this video, we're going to discuss why Gaussian elimination actually works for finding the inverse of a matrix, and then go over a couple of quick examples. So why does Gaussian elimination work? Well, let's think about what it means to be the inverse of a matrix. By definition, A times A inverse is equal to the identity. That's a matrix equation. I can rewrite this matrix equation in a little bit more detailed way as A times the 3 or more columns of A inverse. If I have a 3 by 3 matrix, it would look like this, equal to the matrix built out of 3 column vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1. These are the 3 standard unit basis vectors. This is just another way of writing AA inverse equals I. So if you think about it, we're really taking 3 equations simultaneously. A multiplied times the first vector x, 1, should give us E1, which is 1, 0, 0. And likewise, A times x2 should give us 0, 1, 0, and A times x3 should give us 0, 0, 1. Writing it out, we see the 3 individual separate equations that we're trying to solve simultaneously. AX1 equals 1, 0, 0, and so on and so forth. So, to solve any one of these individually, we would be doing Gaussian elimination on A, meaning we would form the augmented matrix of A, followed by the vector E1, which is 1, 0, 0, and then reduce it until we have an augmented matrix that looks like the identity matrix, followed by another vector x. And what that x is it's the solution to the matrix equation AX equals E1. To make this a little bit more concrete, let's say we had a matrix A that was something simple like 1, 0, 3, 1, and we wanted to find the matrix inverse. Well, this would be my A, and I would augment this, say, with A, E1. And that would be a matrix of the form 1, 0, 3, 1, augmented by 1, 0. And I could use row operations. In particular, here I would use minus 3 row 1 plus row 2 into row 2, giving me the identity matrix. Because this becomes a 0 and this remains a 1, and I would have a minus 3 here. And this vector, 1, minus 3, this is my solution. And it's a solution to a system of equations. The exact system of equations is x plus 0y, 1x plus 0y equal to 1, and 3x plus 1y equal to 0. So that's just a little small example to emphasize what's going on. And so what we have is that to solve all 3 of these simultaneously, in the case of a 3 by 3 matrix, we still do Gaussian elimination on A. We just record the 3 unit basis vectors and the 3 solutions side by side in this process. This yields all 3 solutions as column vectors, and these column vectors comprise the matrix A inverse, which is why Gaussian elimination is what we're doing to find the matrix inverse. So let's move along now and make some observations and do some examples. So I'd like to make the following important observation. Let's suppose that A inverse does exist. A is a matrix, it's invertible, and its inverse exists. When that's the case, you can solve the matrix equation AX equals B exactly. And X is A inverse times AX, which is A inverse B. This is the case where you can essentially cancel the matrix A in the sense that you're multiplying by A inverse. And so this is how you solve for X. You have A inverse, and then you can just apply it to the left-hand side of this equation. So that's going to be very handy. All right, now let's see this observation in action with the following example. For this practice problem, we're going to calculate a matrix inverse, and we're going to use it to solve AX equals B, where A is the 2 by 2 matrix 6, 3, 3, 1, and B is the vector 9, 7. So we're going to do this the long way. There are shortcuts for finding inverses of 2 by 2 matrices, which I'll get to in due time, but we're going to calculate this matrix inverse in the Gaussian elimination process. So the first thing that we do is we form our augmented matrix A, followed by the identity matrix. So here we have A, and here we have a 2 by 2 identity matrix. And we're going to start putting our matrix in reduced row echelon form. The first row operation that I'm going to do is I'm going to divide out the first row by 6 because I like it when my first pivot is a 1. And so that's going to give me a 1, a 1/2, and a 1/6, and a 0 in the first row. So I do have to deal with some fractions in this example. Now I'm going to get to work clearing out this 3. So the row operation that I want to use to do that will be -3 row 1 plus row 2 into row 2. For the next row operation, notice that we can actually add row 2 and row 1 together to replace row 1, and that will have the effect of converting this 1/2 into a 0, which is what we want to do. So the row operation that we're going to employ is row 1 plus row 2 into row 1. Even though I don't have a 1 as my pivot in this spot, I'm going to use that -1/2 to clear out the entry above it. Because remember, I'm working towards something that is eventually going to be the identity matrix with 1s down that diagonal. And then the last row operation that I'm going to do is to turn that -1/2 into a positive 1. I'm going to multiply the second row by -2. And now I'm at my stopping point. Here I have the identity matrix. That means, because I see the identity matrix showing up on the left, that my algorithm has completed, and what shows up here on the right is my A inverse. Now, it isn't strictly necessary, but it's good practice to check your work. So we're going to check that our inverse that we calculated is correct. So for that check, what I'm going to do is take A times A inverse and just verify that when I multiply them together, I get the identity matrix back. So using my rules for matrix multiplication, in the first entry, I'm going to have a 6 times -1/3 plus 3 times 1. In the second entry, I'll have a 6 times 1 plus 3 times -2. In the second row, I have 3 times -1/3 plus 1. And then for the last entry, I have 3 times 1 plus 1 times -2. And that becomes 1, 0, 0, 1. I do get the identity matrix, and so my calculation is correct. So next what I'm going to do is I'm going to use A inverse to solve the matrix equation that we were given in the beginning of the problem, AX equals B. So what is the solution X? Solving AX equals B with this A inverse means that X is equal to A inverse times the vector B. And that is our inverse 1 -1/3, 1, 1, -2, multiplied times the vector 9, 7, which was given in the problem. Up until this point, we haven't used the vector B yet, but we use it here. And this is matrix times vector. So these two entries in the product are worked out by the dot product of row times column and then row times column. And that gives me 4 minus 5. And this is my solution, X. At this point, I'm going to, again, check my work. I want to make sure that AX really does equal to B. And so I can quickly work this out in order to make sure that I didn't make any arithmetic errors when I worked out A inverse times B. And I get 9 and 7 back, and so my solution was correct. This all worked quite nicely, and you can use this type of algorithm to solve a problem like this. But there's actually a shortcut for 2 by 2 matrices, so let's discuss that as well. Finding inverses of 2 by 2 matrices is really easy. If you have a 2 by 2 matrix, A, B, C, D, and A inverse exists, then what A inverse is 1 over the quantity AD minus BC times, that's scalar, times the matrix D minus B minus CA. This is the formula, and you should memorize it. It might be helpful to remember that for the entries along the diagonal, they've been flipped. The A goes to where D was, and the D goes to where A was. The entries off the diagonal stay put, but they get negative signs. This quantity AD minus BC that shows up in the denominator of the scalar, this is called the determinant of the matrix. We'll certainly be talking more about determinants in the future. But for a 2 by 2 matrix, this determinant is AD minus BC. And the fact is, when the determinant of a 2 by 2 matrix, AD minus BC, is 0, that means that the matrix is singular. The inverse of A does not exist. And this formula that I've given you wouldn't make sense at all, because you would be dividing by 0, and you can't do that. However, when AD minus BC is any non-zero number, then this is well defined, and the matrix A is guaranteed to be invertible, so A inverse does exist. Calculating the determinant of a 2 by 2 matrix is a very quick way to determine quickly whether the matrix is invertible or not. Here's a couple of super quick examples of determinants of 2 by 2 matrices. So A is going to be an invertible matrix, and B is a non-invertible matrix. If we calculate the inverse of A, we end up with 1 over 12 plus 7, because that's 3 times 4 minus a negative 7. We apply that to the matrix 4, 1 minus 7, 3. Notice that we've changed the signs of the 1 and the 7, and the 4 and 3 have swapped places, and that produces A inverse, which is just this matrix. B, on the other hand, we can quickly see is not invertible because 2 times 3 minus 6 is 0, so the inverse of B does not exist. Now, you might be wondering, what's going to happen if I attempt to find the inverse of B using the long formula, using Gaussian elimination? Am I also going to be able to see that B is not invertible? Unfortunately, the answer is yes. But let's use this particular example to see what exactly goes wrong. If we go about trying to find the inverse of B using Gaussian elimination, the first thing we would do would be to augment B with the identity matrix. And then we would just go to town with row operations. The first row operation that I would choose to do would be to take 1/2 of row 1 so that my pivot would get turned into a 1. After that, I would attempt to eliminate the 1 underneath the pivot. And doing the row operation minus row 1 plus row 2 into row 2 would give me zeros that show up on the left-hand side of the augmented matrix. But herein I have already reached a contradiction. There's no way that I can produce the identity matrix. So right here I would notice that I'm stuck. I'm not going to get the identity matrix no matter what row operations I choose to use. Why is this a contradiction? At this point, perhaps it would be helpful to think about this augmented matrix as describing for us a system of equations. So let's take this and write it as a system over here. So we actually have two systems of equations if we separate the two columns. So in this first system of equations, we're taking the first column. So 1, 3, 0, 0, and then appended with the vector minus 1/2 minus 1/2 means we would be trying to solve the system x plus 3, x1 plus 3x2 equals minus 1/2, and then 0 is equal to minus 1/2. If we use instead the second column, we get another system of equations, and now we would be looking at x1 plus 3x2 equals 0, and 0 equals 1. Well, this is just loaded with contradictions. 0 is not equal to minus 1/2, and 0 is not equal to 1. So we see that there are contradictions here as well. In terms of the augmented matrix, the problem happened when we had a row of zeros, and then on the other side of the dotted line, we had things that were not 0. So even if you try to find the inverse of B using Gaussian elimination, you'll also reach a contradiction. And of course, we knew that that was going to happen because when we calculated the determinant of B, we saw that that was 2 times 3 minus 6 times 1, which was equal to 0. So it better be the case that the inverse of B cannot exist. The very last thing that I would like to do in this video is to mention a few useful properties of inverses. I'm just going to give you a list, and I recommend that if any of you watching are math majors, that you take a stab at trying to prove one of the items on this list. It's good practice. So the first item is that if A and B are both invertible, then AB inverse is equal to B inverse A inverse. So when you distribute the inverse into this product, you also have to interchange the order of B and A. The second useful property is that A inverse inverse goes back to being A. And then if you take the kth power of a matrix, meaning you've multiplied it together k times and calculate the inverse, then this is going to be the inverse multiplied k times. So this is A inverse to the kth power. If you're dealing with scalar multiplication, a scalar times a matrix A, and then you take its inverse, the effect that it has on the scalar is to invert that. The scalar is a non-zero number, and so 1 over C is a non-zero number. And then lastly, if you take the inverse of A transpose, it's the transpose of A inverse.